my title is actually a triple entendre. It refers to the state of climate science and energy technology themselves. It refers to some of what the real climate science says, which you might find unsettling compared to what you've heard in the media and from the politicians. And it also refers to what we should do about the circumstances we're in. We are told by many people that climate science compels us to make large and rapid reductions in greenhouse gas emissions. On the left is the world's greenhouse gas emissions, and you can see that they are climbing steadily. On the right, we are told, including by Secretary General Guterres, most recently a few days ago at the Sharm el-Sheikh conference underway now, we have to go to net zero emissions by 2050 to avoid the worst effects of climate change. If you think about that phrase for a second, it's not clear what it actually means. But nevertheless, the world is attempting to drive that left-hand curve to zero by the latter half of the century. When you think about what we should do, whether we should do that, something else, the responses have to strike a balance. On one side, we've got the certainties and uncertainties of climate science, the hazards and risks of a climate changing for whatever reason. On the right-hand side, we've got the world's growing demand for affordable and reliable and clean energy. And in striking that balance, you've got to invoke values and priorities, tolerance for risk, intergenerational and geographical equities, as we'll see, and the efficacies and costs of various response strategies. When we look at the historical record, the globe has warmed about 1.3 degrees Celsius since the beginning of the last century, since 1900. And there's the official graph. What's interesting is that comparable warming is projected to the end of this century, 2100. And so one obvious, almost bottom line question, what are the impacts going to be of that warming? Kind of hard to project, but we can draw some lessons from the past. Since 1900, humanity has prospered as it never has before. Despite the warming and despite the global population going up by a factor of 5 to the present 8 billion, life expectancy globally went from 32 years to 72 years, 40 years added. Literacy has gone up tremendously. The fraction of the globe in extreme poverty plummeted from 70% down to 10%, and importantly, relative to the present discussion, the weather death rate is 50 times smaller today than it was at the beginning of the 20th century. For me, it beggars belief to believe that another 1.3 degrees of warming over roughly a century is going to significantly derail that progress. Well, you might say, well, this is over 120 years. What about the last 30 years? Well, there are global damages due to weather since 1990 up till 2020. And what you can see is that as a percent of GDP, they are small and slightly declining, small at 0.2% of GDP. There are other studies that say that the mortality and economic loss rates have also plummeted in recent decades. This is not a signature that we have broken the climate. A lot of text on this slide. I'm not going to go through it, but they are all direct quotes from the most recent UN report on the climate issued a year ago, August. Most people don't read that report. At best, they'll read the summary for policymakers, and more usually they'll get it out of the media. And I can tell you that the report says some really interesting stuff that nobody or hardly anybody ever finds. For example, there are no detectable long-term trends in hurricanes. There are no detectable long-term trends in mid-latitude storms. No detectable trends in extreme winds. Yes, we've seen more heavy precipitation over land over the last century, but globally, no detectable long-term trends in floods, droughts, etc., etc. Okay? So again, hard to believe that we have broken the climate. Nevertheless, the media exaggerate all of this confusing weather with climate. I published a piece in the Wall Street Journal earlier this year in February about Greenland's melting ice. You can find press releases from NASA and from The Guardian in the UK that says Greenland's ice sheet is melting 7 times faster than it was in the 1990s. And you read through the text and it says, well, the rate of ice loss has risen from 33 billion tons a year to 254 billion tons a year most recently. Wow, sounds like we're in real trouble. But when you look at the actual data, it's on the right. And yes, there was a rise from 1990 to 2010 or 2012, but there was a comparable rise and a high variability much earlier in the century. And in fact, the more recent years have been coming down, and I can tell you this year it will be even lower. We're almost at the end of this year. And so you can and the media do, misrepresent shorter-term trends in order to persuade you rather than inform you. Let me talk about one bottom line impact of climate change, which is economic impact. If you go to the 5th IPCC report, UN report issued in 2014, buried back in almost the last chapter of one of the reports, it says for most economic sectors, the impact of climate change will be small relative to the impacts of other drivers. Changes in population, age, income, technology, prices, lifestyle, blah, 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 will have much more of an impact on economic well-being than a changing climate. And in fact, all of the scenarios that the UN uses to describe future emissions, economy, population, and so on, all of them have significant economic growth. Since that time, there's been a lot of work. I'll just show you one example of a summary from a paper by Richard Toll a couple months ago. He's analyzed maybe 50 different ways of projecting economic impact for the globe. This is for a warming of 4.3 degrees by 2100. That's more than twice what the Paris guardrail is and almost 3 times what the 1.5 degree limit is. And you can see there are 4 different ways of trying to project what's going on. 3 of them more or less agree with one another. And what's remarkable is that the vertical scale is in percent. 3, 4, 5% impact on the economy in 2100 for a warming that is 4 degrees. Where is the climate crisis? So, of course, you still might fret a little bit about the fat tails on these, the one divergent method, which gives answers between +10 and -50, you can discard for good reason. I won't go into the details now. Talk about it in the questions if you want. You still might fret. These are only 1 sigma error bars. Maybe it's going to be worse. And those of us in the developed world have the luxury of clutching our pearls over that. But 6.5 billion people in the rest of the world do not. So let me turn to that issue and ask, are large and rapid reductions desirable? Here is an almost recent projection of the global population out to mid-century. It shows that we'll top out at about 9 billion people. We're currently at 8, as we've just officially passed 8 billion in the last week or 2. And you can see that most of that growth is in Asia. It's a fundamental law of society that as people get wealthier, they use more energy. This is a graph of the energy use per capita annually in gigajoules per year against the GDP per capita in constant dollars. There's one dot for each year for a great variety of countries, and this ranges from 1980 to 2017. So you can get a sense of almost 40-year trends. There are some countries in the upper right, the US, Norway, Canada, that use a lot of energy per capita, but they also have a higher GDP. There's a whole raft of countries in the middle, Europe, Japan, that have about half the energy use per capita, but a comparable GDP. But what is disturbing about this chart is that there are 1.5 billion people in the upper right, but there are 6.5 billion people in the bottom, and their energy use is going to increase as they develop. Energy poverty is awful. All right? You can see a picture on the left here, cooking with what's called traditional biomass, in a formal sense, wood and dung. Air pollution kills 2 million people a year from the indoor smoke. People on the right studying by candlelight, pretty awful conditions. The numbers are just about as bad. The US per capita consumption of energy is 30 times that of Nigeria. And there are 3 billion people in the world who use less electricity every year than the average US refrigerator. And so when you fold that development together with the population, you're going to get a strong increase in energy demand, as shown on the left. Again, quads, some measure of energy consumption per year. You can see it's going to go up by about 50% from now until the middle of the century. And where is that going to come from? Of course, it depends on policies and technologies, but under current policies, you can see that while renewables, namely wind and solar mostly, will grow, fossil fuel use will grow even more strongly, and most of the world will, in fact, remain powered by fossil fuels. In fact, if you look over the last almost 30 years, the fraction of the world's energy derived from fossil fuels has remained just about constant at 80%, despite some growth in wind, solar, thermal, geothermal, and so on, which are the rainbow of curves down at the bottom. This is particularly disturbing because over the last decade, the world has spent almost $4 trillion to try to deploy wind and solar, and that number, 80%, has hardly changed at all. And so what we're going to see, most likely, is a strong growth in emissions due to the development of the developing countries, because fossil fuels are, in fact, the most reliable and convenient way for them to be getting their energy, even as the developed world, OECD, might be reducing its emissions. I like to quote a statement by a guy named Anthony Downs, who was a social scientist working in the late 60s in UCLA. He eventually moved to Brookings. And he was watching the smog in the Los Angeles basin get worse and worse as more and more people could afford automobiles. And he said, the elite's environmental deterioration is often the common man's improved standard of living. That's a good description of what we're facing right now. And so when we say the science compels us to reduce emissions, the response from the developing world is, what do you mean, us? You see that playing out in remarks at the Sharm el-Sheikh conference in real time. Just read the paper today and yesterday. A couple months ago, the Indian Prime Minister said the colonial mindset hasn't gone. We're seeing developing nations, seeing from the developed nations that the path that made them developed is being closed for developing nations. And the Nigerian president in June said Africa is being punished by the decisions of the Western countries to end public financing for foreign fossil fuel projects by the end of 2020. We're going to continue to fight. We have fossil fuels that should be exploited. And so, there is a moral dimension here, as Alex Epstein has pointed out. How do you balance this need to improve the lot of most of humanity against the perceived need, urgency to reduce emissions? There's another moral issue here. By raising alarm unduly, and I think I've shown you that the alarm is undue, we have robbed young people of their optimism. You get these protests, Just Stop Oil, I think, in the UK has been the latest, throwing tomato soup at artwork and so on, sticking themselves to the roadway. And, even influencers like Miley Cyrus are saying, I don't want to have children and bring them into this kind of planet. That's just terrible. It's unwarranted, it's unjustified. By the way, I was particularly pleased. This is the first image of Miley Cyrus I ever had in one of my presentations. All right, so you say, all right, well, maybe we should do it anyway. Is it possible? Can we make large and rapid reductions? This is a graph of how the U.S. got its energy over the last 70 years. And it shows that at the beginning it was wood, and then it was coal, and then oil took over, and gas more recently, and then renewables are that little blue thing at the top. Okay? And yes, renewables are growing, wind and solar and so on, but you can see that by and large, technologies pile on one or the other. They don't reduce the others. The only exception to that is the shift over the last couple decades from coal to gas in generation, and that is due to the advent of fracking, which makes abundant and inexpensive gas available to the country. So the world is moving to all electric. We're going to electrify transportation, we're going to electrify building heat, and the image I like to use is that one. Wile E. Coyote has suddenly realized that there are some things that are going to spell a very bad future for him going forward. Let me tell you what some of those things are. The electrical grid is central to all of this. We're going to run electric vehicles. We're going to change the building heat to heat pumps. And I like to talk about this trilemma or troubled triangle that the grid has. We'd like our electricity to be affordable. We like it to be reliable. We also would like it to be clean. If you want to be affordable and reliable, gas and coal are what you want to be doing. If you want it to be affordable and clean, wind and solar. But if you want it to be clean and reliable, then it's either storage, big batteries, fission, nuclear power, or carbon capture and storage. You cannot have at the moment all three. Let me show you why. Here is some real data from the UK. It shows the wind generation for 6 months at the end of 20 and 21. And you can see long gaps up to 11 days, as shown on the right, where the wind was not producing hardly at all. This is a very important phenomenon in renewable heavy grids. So important that the Germans coined a word for it, Dunkelflaute, which means dark stillness. And managing Dunkelflauten is central to having a renewables heavy grid, and it's not so easy. By the way, Texas, I can show you the same data. You see 3 weeks at a time in the summer where Texas wind doesn't produce at all. So you ask, how could I build a grid that's got enough firm power, reliable power, to be able to ride through those Dunkelflauten? And the answer is you have to spend at least as much money as you spend on wind and solar to provide the backup, whether it's batteries or small nuclear or gas with carbon capture and storage. And my former colleague at Caltech, Ken Caldera at Stanford, and Jackie Dowling have done a series of studies using the real weather data for 40 years at the county level in the US at 1 hour intervals. And you can ask, how much backup do I need? And of course, translate that into a cost of electricity. And you see on the left, natural gas is by far the cheapest way of generating electricity. If you want to go in the second group, nuclear heavy, well, it gets somewhat more expensive. But if you go far to the right, you can see that if you want a lot of wind and solar, the orange or the blue, the costs go up by more than a factor of 2, actually. And so the notion that renewables are going to reduce the cost of electricity is just nonsense, because not only do we want electricity, but we want it reliably. The federal standard is 99.99%. Right? And to get that reliability, you need a tremendous amount of backup. Renewables have other oops issues that Wile E. Coyote has suddenly realized. Land use, for example. Wind takes many times more land than geothermal, nuclear, or coal, even including the mining. There's a lot more stuff in renewables because you have to build big structures to capture diffuse energy, whether it's wind or sunlight, and those structures have to be very efficient. So you get to use fancy materials, not only copper and nickel, molybdenum, rare earths are really important. And you can see that for transportation, an electric vehicle takes 7 times as much critical materials as does an ordinary internal combustion engine. And for power generation, it's almost an order of magnitude more in terms of fancy stuff. Another problem which has come to light in public discussion more recently is that those exotic materials, many of them come from unusual and uncomfortable places. China at the moment dominates the processing of rare earths, lithium, cobalt, and so on. So if you want to deploy these new energy technologies at the pace envisioned, you're going to have to change these supply chains, and the costs are going to go up because energy and environmental standards are pretty cheap in China, which is how they can do all of this. All right, let me go through some energy specifics real quickly. It's pretty hard to predict a lot of this stuff, but you can try to make some predictions that are not so broad as to be useless, but also not so specific as to be wrong. So we're going to see a rise in coal. We're already seeing that. Coal use in the last few years has surged because of the energy crisis, induced in part by the Ukraine situation. We'll then see it decline. Coal is not a great fuel. It's got local pollution issues as well as greenhouse gas emissions. We're going to see a lot more gas. The world has plenty of gas, not only in the US. Europe has 50 years worth of gas at its previous current consumption rate if it would go to fracking. And that's really important for energy security, lower greenhouse gas emissions, but there is a deep resistance to doing it. Hydrogen, I think hydrogen for light-duty transport is not going to happen. There are too many barriers. Hydrogen for heavy-duty transport, trucks, I could imagine, trains, not airplanes, that would be a bad idea. But for grid storage, there's something called power to gas to power, where you take excess power, electrolyze water, make the hydrogen, store it, and then burn the hydrogen when you need the electricity. Round-trip efficiency is not great right now, only about 50%, but we can work on it. Probably the most viable way of grid-scale storage, in my opinion. We're electrifying light-duty vehicles, passenger cars. That's underway already. I worry about the charging infrastructure and, as I said, the critical materials. In temperate climate, heat pumps can do a pretty good job. If you get much further north than this, I think there are issues. You're going to need the natural gas as a supplement. Wind and solar are going to grow, but I don't think they're going to get to more than 80% because of this reliability issue. Fission, small reactors will work, most likely deployed outside of the US first. That's where the demand is, and they're a little bit more adventurous with their energy systems. Fusion will work in a scientific sense, but it has to be cheaper than the alternatives, and that's going to take at least 20 years, I would say. The grid is maturing. the informatics overlay on the grid, sensing, control, two-way flow of energy. That's all underway. I was just at PNNL yesterday and the day before, and they are experts in analyzing and controlling the grid. I worry, once you've got beyond the transmission, I worry about the distribution infrastructure. So I was talking to Con Edison in New York a couple weeks ago. They are deathly afraid that if heating oil and gas get banned from heating buildings there, never mind the electric vehicles, they're going to have to at least double all of the underground cabling and the distribution, the transformers and the substations that they have under Manhattan. That's a multi-decade, expensive, disruptive undertaking. Supply chains, we've already talked about that. I'm not going to say more. There will be new waste streams. Batteries. The batteries have a finite lifetime. They wear out. There are businesses being started to recycle the batteries and capture the critical materials there. Turbine blades need to be recycled, solar panels, et cetera, et cetera. So my hazy view of what energy for the next 30 years will look like. If you look at this analytically, adaptation is going to be the dominant response that the world will make. Adaptation is agnostic. It doesn't matter whether the climate is changing for human or natural reasons. It's proportional. We will adapt more as the climate changes more and less if it changes less. Adaptation is local, and so it's palatable politically. If you can tell a country, hey, we've got to build a seawall, tell a city, they can understand that. Whereas if it's something that's going to happen halfway around the world and 2 generations away, it's pretty hard to make that sell politically. Adaptation is autonomous. It's what societies do, as you saw from that progress from 1900 till now, and it's effective. All right, I'll close up a little bit about what we need to do. There is a lesson from what happened in Sri Lanka about 1.5 years ago. For those of you who weren't following the story, the Prime Minister there banned rather suddenly chemical fertilizers for environmental reasons, local nitrogen and also greenhouse gases. And it took only a few months before the economy crashed entirely. Agriculture went down, foreign exchange went down, they didn't have enough money to buy fuel and so on. And there's a wonderful quote from Ted Nordhaus and his co-author in Foreign Policy earlier this year. The farrago of magical thinking, technocratic hubris, ideological delusion, self-dealing, and sheer short-sightedness that produced the crisis in Sri Lanka implicates both the country's political leadership and advocates of so-called sustainable agriculture. If you just change the wording slightly, I think you get a pretty good picture of what's going on today with respect to energy, both in Europe and in the US. And I'd leave you, before my last charts, precipitous emissions reductions are far more dangerous than climate change itself. So what do we need to do? First of all, as a scientist, someone used to giving scientific advice to decision makers, let's not Gruberize climate science. What do I mean by Gruberize? There's Jonathan Gruber. He's a professor at MIT in economics. He was one of the principal architects of the Affordable Care Act, Obamacare. And at a conference shortly after things were all passed, he said lack of transparency was a huge political advantage. It was really, really critical to getting the Affordable Care Act passed. At least one key provision was a very clever basic exploitation of the lack of economic understanding of the American voter. And I can tell you as a professor and an advisor, that's just so wrong. When we conceal the underlying understanding from non-experts, we take away their right to make fully informed value decisions. We distract from more urgent needs, and boy, do we have many more of them than climate. We tarnish scientific input in other important matters like pandemics. And as I've told you, we depress young people. And that's why I wrote that book about a year and a half ago, to just try to give people a real sense of what the real science says. Almost everything in it is right out of the official reports or the peer-reviewed literature or the original data. All right, so after criticizing all of this, people like to know, well, Koonin, what would you do? First thing is, let's cancel the crisis. There is no climate crisis, but let's acknowledge that there is a problem that we need to deal with on some longer time scale. We need to better represent the science to non-experts. I favored red team reviews of the assessment reports. We need to promote energy and climate literacy among the public and decision makers. We need to keep watching the climate. We are looking for small shifts over decades, so precise, continuous observations are really important. Let us not constrain the developing world's energy supply. I would assert again that that is immoral. We need a greater focus on adaptation, costs, a framework for doing that, and promoting the development and resilience of the developing countries, which will require that they use more energy. Develop and demonstrate emissions-light technologies. Bill Gates is right that the solution to all of this is going to be technologies that are no more expensive than emitting technologies. My own favorites would be fission, grid-scale storage, batteries, non-carbon chemical fuels for the transportation we can't decarbonize. And then get together a group of technologists, business people, experienced energy regulators, and behavioral folks to formulate a graceful decarbonization plan and implement that as needed. You know, we cannot change energy systems suddenly in ill-conceived ways. That is so disruptive, as we've seen already in Europe, Texas, the UK, California. With that, I'm happy to take comments or questions. Thanks for your attention.
Just a question, Tom Marseille, just a question on your last point on your last slide. You suggested we still need to figure out how to decarbonize, essentially, but you sort of belittled or sort of made the point that that wasn't necessarily what we had to do. Could you comment on that, please?
Yeah, I think long term, on a century scale, we should be decarbonizing, but it's going to take a long time. You know, the very last sub-bullet said implement as necessary. So.
Marianne Tupy, Cato Institute. I'm a big fan of your work.
Thank you.
I wanted to ask you, what did the reception of your book teach you about the environmental movement?
Yeah.
Did they engage with the science? Was it mostly ad hominem attacks? And if it's ad hominem attacks, I would like to ask you, is the extreme environmentalist, is it just an ideology? Or does it speak to something deeper? A desire of people for a sense of meaning, for a sense of self-application, a structure, whereby the environmental ideology or even quasi-religion can provide them with all those things. Thank you.
So I'm just a physicist, okay? All I can do is deal with numbers. If you ask my wife, I'm particularly bad at people issues. Let me just do some facts, okay? We've sold 200,000 copies of the book. It has, thank you. The French translation just hit the stands a day or two ago. Really good reviews in some of the major French papers. Wall Street Journal publicized the book, okay, they're ideologically disposed perhaps to do that. Not a word in the New York Times or Washington Post. Mm-hmm. There were a couple of climate scientists who wrote 1,000 words in Scientific American, most of them ad hominem attacks, 3 scientific points that were based on a review of the book, not on what the book actually said. Many of them hadn't actually read the book. I wrote a rebuttal to that. Scientific American refused to publish it. You can find it on the website. You know, the short answer is for some fraction of the population, the facts don't matter. But I think the bright spot in all of this is that ultimately the laws of physics and economics do affect you. Wile E. Coyote will fall. And I think the current energy crisis has awakened people to the need or to the primacy of reliability and affordability over clean, and will induce them to have a harder look at what the science really says. Okay.
Mike Stevens, Entropy.org. Since our only defense against factions are facts, and there appears to be little logic in ecological, can you inform us, we need these facts, and can you inform us about the conversation about, is the ocean rising or the land falling? Can you comment on isostatic rebound, because we don't know enough about it, and gravity wells as to sea level?
Yeah.
Thank you.
So, sea level is one of my favorite topics. I like to, first of all, it's complicated, okay? The hydrological cycle moves 900 millimeters a year of water. It's the average rainfall. We're talking about rises in the ocean of 1/10 of a millimeter a year as being significant. Sea level rise varies a lot as you go around the world's coasts. I pay attention a lot to what happens in Manhattan. At the Battery, the southern tip of Manhattan, there's been a tide gauge measuring since the mid-19th century. And so we got a pretty good record, some gaps. And what you find is, first of all, the tip of Manhattan is subsiding at about a millimeter a year. That's measured by GPS, and it's not thought to change much over centuries. The second is that the rate, I wish I had control of my charts because I have all this in backup charts. The rate of rise, on average, is 3 millimeters a year. That's a foot a century. But the rate goes up and down with about a 60-year cycle. At the minimum of the cycle, it's less than 2 millimeters a year, and at the maximum of the cycle, it's up to 4 millimeters a year. So there's dynamics in the North Atlantic that are modulating all of that. Is any place going underwater rapidly? There are some places that are subsiding tremendously. Houston is subsiding, or the Gulf Coast, they're subsiding a lot. That's due to water withdrawals, nothing to do with the glaciers. The average ocean rise is 3 millimeters a year globally, but there are a lot of local variation.
And isostatic rebound?
Oh yeah, it plays a role, okay? I mean, in Scandinavia, the ocean is actually going down because the land is going up. And then there are gravity issues. If Greenland melts, then that changes the gravitational attraction of the ice sheet and will change things. It's complicated at the local level. At the global level, we're seeing thermospheric expansion. So the thermal expansion of the ocean as it warms up, and it is warming up, is a major player. And then some melt from Greenland, although highly variable, as you saw, mountain glaciers and so on. Good number to keep in their head is 3 millimeters a year, a foot a century.
David Kruger, I've been following the development of redox flow batteries for the last several years, and there seems to be great promise in that technology. Things are going well, and I wonder if you had any commentary on that.
Yeah, I had grid storage as one of my promising research areas. The problem with flow batteries generally, I think, is scale. Okay? You've got to have the grid run on firm power for 10 days at a time. And if you think about the scale of storage you need for that, because the redox batteries are pretty dilute, that's the problem, right? It's not like lithium-ion batteries are more dense, but still not as dense as hydrocarbon fuels. So good, promising area to be working on. Not going to be good for transportation. It's too big and too bulky, but that's a good thing to be doing for grid storage. Okay? Yeah.
Cor Caden. This group here is very largely interested in technological aspects, and I'd like to bring up two of them. One of them is that if you look at the energy per capita used in the United States, comparing what it was in Ben Franklin's time with what it is now, we use approximately 3.5 times as much energy per capita. It's a very, very small number considering the fact that they didn't have a lot of EVs back in Ben Franklin's time. And they kind of had a shortage of air conditioners as well. The other technological thing that I think is sort of generally unknown to a lot of people in here is that Pratt & Whitney developed some years ago single crystal, I guess they were titanium super alloys to be used in turbines. And the upshot of that is that now they can use those in natural gas-fired power plants, and the larger ones are getting 60% efficiency. That is 60% of the energy that's in the natural gas becomes electricity. And so the reason to bring those things up is that they are speaking to advances in technology, making things generally more efficient all the way through.
Absolutely. Although I would caution about efficiency. Efficiency always doesn't lead to conservation.
You are
right?
correct.
So it's maybe worth reciting a little bit about Jevons if people don't know about that. So Jevons was an economist working in mid-19th century UK, and he was watching steam engines get better and better, and he started to realize that as they got more efficient, coal consumption would actually go up because steam engines would appear in more places. And so you have to be careful about this thing called rebound. Efficiency doesn't always lead to reduction in energy use.
You're quite.
All right, I think we have to maybe.
No, you have time for one more question, but we do need to. We have to reorient the stage. So.
Okay, good.
Michael Cook, thanks for a really good talk. Did you say that nuclear energy was going to be economical in 20 years?
No, I don't think I said that.
I thought I heard you say that.
No. Fusion. I said it's going to be at least 20 years after we get it to work. There are issues with it. I can go into them if you like. But
well, someday. Sure, I'd love that. But I just think that made me more optimistic to hear that. That surprised me. Nuclear fusion in 20 years will be economical?
I would say, no, I think what I said was it's got to be better than the competitors.
I thought I heard you say it will be
economical.
No. Oh, please.
No. I give you a long discussion of the issue.
Let's hear it for Stephen.
Okay.
Koonin.